we continue the lectures on Laplace Perron's method regarding the existence of the solutions of Dirichlet boundary value problem. So what we have introduced in the last class is we have defined basically the sub and super functions or sub harmonic and super harmonic functions for continuous functions. Earlier the definitions were for the C2 functions, but of course using mean value theorem you can define for continuous functions. But last week or last lecture what we have defined for continuous functions using the concept of maximum principles. And later at the end of it, what we have done is that we have defined a class of a subfunction. A subfunction, and for such functions we are defined. So let me quickly recall. We are defined a few properties regarding this continuous function, regarding the harmonic functions. We have seen a maximum principle, and then we have seen a harmonic lifting, because if you have a subharmonic function for any ball, you can redefine to be as a harmonic function using the Poisson integral. So if you are given a continuous subharmonic function, and then you can use that continuous function value on the boundary, you can define the harmonic function using the Poisson integral, and you define in that ball this harmonic lifting outside. It is that subharmonic function. This function as in omega, it will be subharmonic but harmonic inside the ball. We also seen another property. All that we'll be using now. A maximizing subharmonic function is a subharmonic, and minimizing superharmonic functions are superharmonic, but not the other way. So the minimum of a subharmonic function need not be subharmonic. And then what we have done is that we are at the end of the lecture last class, we have defined what is a subfunction. A function g is given a continuous function. We say that v is defined in omega is a subfunction which is relative to this function omega, and of course continuous function subharmonic. The important property we have defined is v also less than or equal to g on d omega is what we have defined there, and we denoted Sg is the set. So let me recall that one. Sg is the set of all Sg is equal to set of all v in C omega bar, the set of all continuous functions, which is v subharmonic and v less than or equal to g on the boundary. Harmonic in omega and v less than or equal to g on the boundary of omega. And using this, now we are going to define what we already defined, a function ux, which is what we are going to get the solution. So let me define once more. Ux equal to supremum of v, and v is in Sg. Okay, so this is my definition of u, and what we are going to show. So there are this Laplace thing satisfies basically three properties. It's a continuous function, subharmonic, and v less than or equal to c, and we are maximizing that u, and you expect that to be a thing. What is a maximizing function? So you have to prove some important thing. This, what about whether this Sg is so the immediate claim, this is a trivial claim, Sg is non-empty. That's very easy to prove. Sg is non-empty. Okay, Sg is non-empty. What you do is that you take infimum of g over x in d omega. G is a continuous function, d omega is compact. This is a bigger than, it cannot be minus infinity. So you choose any constant, c, such that c is less than equal to infimum. This is bigger than minus infinity. Okay, so it cannot reach, otherwise infimum can reach minus infinity. So this is a constant function. So if you define Vx equal to C, which is a constant function, then this belongs to Sg. So any constant function less than this minimum is in the class of Sg. So Sg is a non-empty function. So that's very important to begin with. Okay. Now we will state the main theorem. Main theorem. This U, what we have defined now, going to be your solution to your Dirichlet harmonic function. Not the boundary value problem. It is going to be that boundary value problem, but it takes some time to prove. The proofs which I am going to present is bit of technical, so you have to follow it very carefully. Okay, so let me state this thing. Let G belongs to d omega, C of d omega. C belongs to C of d omega, and Sg be as above. Sg is the set of all subfunctions. Be as above, and define U as U again as above. Then U is harmonic. Okay. That is, it solves the problem. That is not the boundary value problem. Proving U equal to G on the boundary requires little more effort. This itself, the proof is a bit delicate proof, so you have to be carefully follow this one. So let me try to give the proof. Sometimes even if it is delicate, it is nice to learn the proofs. Okay, so it is good to learn this proof. Okay, so we will prove in step by step. The step 1 is U is well defined. This is important first to see that, because U is defined as a supremum function. You see, U is defined as a supremum, so it's possible that it can go to plus infinity. You have to show that that is not true. Okay, so you can define. So take any V in Sg. Okay, take any V in Sg. That implies your V of x less than or equal to Gx. Okay, on d omega. Okay, and V is also subharmonic, right? Because V is subharmonic. So that implies Vx is less than or equal to supremum of Gx, where x is in omega, x is in the boundary of omega. This is true for all x in omega. This is by mean value property, not mean value property, maximum principle. So the maximum principle tells you that V is in fact less than or equal to thing. So you see, V is less than or equal to supremum over G. Any x is a supremum, forget it. So in d omega, the supremum of that one. So that implies that is a finite quantity, is always less than. So this is V is arbitrary. So taking supremum over V, now taking super V, right? This is for any V, this is true. Taking super over V, you get Ux is less than or equal to supremum over G. Okay, with x is in d omega. This is a finite quantity, which is finite because it's a thing. So therefore you cannot be plus infinity. So that's a first step. So we will do the second step. Step 2, the proof of harmonicity is delicate. Proof of harmonic is very delicate. So to prove very carefully. So what we are going to do is that, so you have a domain omega, you want to show that, you have to prove that Laplacian of u equal to 0 in omega. So what we will take, you take any ball inside, take any b, take any ball b contained in omega. Okay, and we show, that's enough, we show Laplacian of u equal to 0 in b. Okay, since b is arbitrary, we get Laplacian of u equal to 0. So we are going to show Laplacian of u equal to 0 in b. That's what we are going to show. Okay, so that's what we will show. This is your b. Okay, so that's what we are going to do in step 3. Slowly, maybe step 4. So you go to. So to show that for any domain, any ball you take it, you show that Laplacian of 0. So what we will do, so let me give you an idea and then we will prove it. The idea is, take a B is in Euclidean space. So take any countable dense set. Okay, countable dense set. Since it is countable, the dense set you can write it like this: x2, x3, like that. Okay, in B, and construct, these are the ideas, construct V which is harmonic. This is what we are going to show, harmonic, and v of x, u of xk is equal to v of xk. Okay, then by continuity, of course you don't know even u is continuous, that's a different issue. Then by continuity, prove u identically equal to v in B. Since V is harmonic in V, V capital V is harmonic in B, you show that, you conclude that U is harmonic in B. So let's go to the step, that one. So take any, so you take that set. So first claim is you want to do how to construct this B. Okay, so that's a step 4. Step 4 is a claim. So we will do a claim now first. Okay, claim for a sequence. I don't say that it is a dense set. So you take for any sequence. We need this to be proved, not just for dense set. For any sequence x1, x2, etc. So this is a sequence xk. There exists a sequence. There exists a sequence Vj in Sg. Okay, so there exists a sequence Vj in Sg such that m less than or equal to Vj of x. I will write down what is a less than or equal to m for all x in omega, where and Vj of x xk converges to u of xk as j tends to infinity, and this happens for all k. Okay, so all these you are able to construct Vj in Sj. Of course, you can always construct fixed k. So you look at this function u given. You look at, so for this is for all x. So once x is fixed, you can always find a sequence in Sg which converges to that. But you want that sequence independent of x, basically. That's what it shows here. You want that for a given xk, that's what we are doing. Given xk, you should be able to find Vjk. So before that, let me write down what is your m. M is equal to your infimum of g over d omega, and capital M is equal to your supremum of G over d omega. Okay, so that's what you are doing to. So first observe, so you let me go to this. So you need a proof of this claim. So that's what you are going to do it. A proof. By definition of supremum, okay, supremum, because ux is the supremum, right? For each k, for each xk, there exists vjkx. So the constructing a sequence is easy. Vjk of x or vjk belongs to Sg. Okay, you can find vjk belongs to Sg such that vjk of xk converges to ux. This is just infimum. So u of xk as j tends to infinity. So obtaining a sequence which depends on j and k is not that difficult. And what is more difficult is that thing. So you do not exactly a diagonalization procedure. So but we will do something slightly different. So you define Vj. Of course, this is Vjk is in Sg. So it all you get it is less than or equal to, get all that properties for Vjk you get it. So we will define Vj of x is equal to maximum of Vj1 of x. You do a maximizing, because while maximizing the subharmonicity will not change it. So you will get it Vj of j of x, and of course then this will be belongs to Sg by this maximizing thing, and because each Vji belongs to Sg. Okay, further, so you see immediately further, if we for any k, and if you choose j large enough, j greater, because you are trying to see what is the limit of Vj. So if j greater than k, what you will get it Vj k of x. No, Vj of x. Vj is the maximum. So Vj of x less than or equal to Vj k of x. That's of course less than or equal to ux. These are all less than or equal. Vj is also is the supremum. From here also you get it all this Vjk from j, because it's a supremum and u is supremum. You have this Vjk is always less than or equal to ux, because ux is defined as the supremum of such quantities. Okay, so this you have it ux. So now Vjk of x converges to u of xk. That immediately implies your Vj of xk also converges to u of xk, since Vj of xk converges to Vjk of xk converges to u of xk. That you are already known that. Since this converges and it is bounded with that one, so sorry, so I have written in a wrong way. Vj is the maximum, so the k should be here as I wrote here, and Vj of x. So Vjk of x converges. Since this is converges, so the sandwiched functions also converges to that one, and so that's hence the claim. So you have proved that. So this is the claim. So you keep this claim now for any sequence. So you take your Vj. Okay, now you use the harmonic lifting. Next step, step 5. Okay, you take the step 5. Now you look at the ball here. So you have your domain here, and you have your ball here. This is your B, any ball here. So look at these boundary values. So you have Vj everywhere. So you take your ball here. Okay, so you have your ball here. Use this value. So use this value here at Vj. Okay, and when you have, so you consider Vj restricted to the boundary of the ball, and let Vj be the harmonic lifting. Be the harmonic lifting. Okay. So you already seen that when you Vj is given, using this you can define the Vj inside. And you can define Vj by the harmonic lifting, because you know that how do you define this Vj of x? In B you define Vj of x is equal to the boundary of B, the k of xy and Vj of y dy. Okay, and which also gives you immediately, you can, because xk is a sequence in V everything, so that immediately also implies your Vj of xk, you see, converges to this integral Vj xk converges to this one, and you will get immediately, and Vj is bounded, converges to V for some V. Okay, so Vj not xk, V of x, since for some V harmonic, because Vj's are harmonic in V, harmonic in. So understand this harmonic lifting. So you have your harmonic in B. Okay, so you are working only in B. So you have a harmonic lifting, not anywhere else. And Vj is harmonic for some V harmonic. Because Vj's are bounded. Because this bound is always preserving and all that. Vj of x less than or equal to M. So you have your bound here. So you have your harmonic lifting immediately. Okay. So in particular, and you can show that V of xk. But Vj of xk is converges to you have moreover you have this also. Moreover, you have Vj of xk converges to U of xk. Okay, that follows again from the definition, because Vj of xk is k of xk y Vj of y, that will converges to integral k of y Vj of y. That's nothing but your V of U of x. You get immediately what's your U. So because your Vj of xk converges to U of xk. So you see, so you have because of this convergence Vj of xk, you will get your Vj of xk also converges to U of xk. Just check. If you are not convinced, please check. So that implies your V of xk. So this is the AM. So V of xk. Okay. So U of xk for all k equal to 1, 2, 3, etc. So you have U of xk converges to that. Okay. So that's good. So what if we conclude? So what is the conclusion? Conclusion: given any sequence, x1 etc xk, x2 etc xk, there exists a harmonic V. There exists a harmonic V in B such that V of xk is equal to U of xk. This happens for all k equal to 1, 2, etc. Of course, the important point is that V depends on the, V depends on the sequence. So sequence xk. So immediately you can, of course, V is harmonic, but V only coincides with on that sequence. So immediately you can conclude about the harmonicity of U immediately. So what we need, an important thing, is what we call it the continuity of U. So the next claim, U is continuous. Okay. In B. That's all. We are working with only in B. Okay, let me give the proof. That. So choose. So these are the steps. Choose xk. You want to show U is continuous. So for any converging sequence, you have to show that U of xk converges to U of x. So without loss of generality, after taking this, without loss of generality, take x1 equal to x. That will not change the convergence, right? x1 equal to x. So if you take any sequence xk converges to x, you replace that x, the first element, by x, or you add the first element as x. That will not change the convergence at all. So corresponding to xk, let V be the corresponding, let V be the corresponding harmonic function. So every sequence you have seen a harmonic function satisfying this property. Let V be the corresponding harmonic function. Corresponding harmonic function. This is a small trick. Harmonic function. Okay. Then V is continuous. That you know, because it's a harmonic function. V is continuous. That implies V of xk converges to V of x as k. Now it's as k tends to infinity, because it's with respect to k instead. Now V of xk is uxk. So this is nothing but uxk. So uxk, V of xk by V of x. So U of xk converges to V of x. Okay. But V of x, what is x equal to x1? We have taken. So V of x is nothing but V of x1. I can replace. I told you this is a simple trick. But V of x1 is nothing but U of x1 by the construction of V. But then now again replace x by x1 by x. This is U of x. You see, this is a very small trick playing. So U implies, that implies your U is continuous. So now your proof is almost done. This is the one important thing, proving. So after that lifting, using the lifting, we proved U is continuous. Now the final part. Final part. Okay. Now take xk, sequence xk, take xk sequence which is dense in B, which you can do it. You can always take, because B is a subset of Rn. Okay, and you know that you can choose a dense set like R. You have the rational which is countable, which is dense there. So even in Rn, you can always choose the dense set which is countable. So sequence which is dense in B. Okay. Okay. For this, take the corresponding V. Now take the corresponding V. Corresponding harmonic V. Okay. What it will say, that is V of xk is equal to u of xk for all xk, for all k. Now u is continuous. Earlier we could not conclude because there is no continuity. Now as v, u are continuous, conclude that v of x equal to u of x for all x in B. You see, because it's dense. It's a very cute, nice proof. A bit in a delicate way we are proving. That implies u is harmonic in B. Since B is arbitrary, we get u is harmonic in omega. Okay, so that proves in a sense the solution existence of, so that proves the theorem, completes the theorem, right? Completes the theorem, existence of a, so that proves existence of a harmonic function, proves existence of a harmonic function, existence of a harmonic function, function u in omega, such that you have only this one, u less than or equal to g on d omega. You are not proved that u equal to g. That requires some regularity. Okay, to solve boundary value problem, we need u equal to g on d omega, which requires regularity. In general, you may not be able to show that. You will see, in fact, you will see some necessary and sufficient condition soon of the regularity for a solvability for all g, regularity of d omega. Okay, what we are going to introduce, this actually so this turns out to be a, this turns out to be a, it turns out to be the existence of a local, existence of a local subharmonic function at the boundary, local subharmonic function. So it reduces everything to that minimum thing, local subharmonic function at the boundary points, preserving the negative sign. That's very important, preserving the negative sign. Such a thing is called barrier function. So we prove we demand that barrier function. So basically you have a domain here, and then every point you are looking for some neighborhood. On this you will look for a negative. This may not exist all the time, so that's going to be the assumption, negative subharmonic function. harmonic function. And this should happen for every point in some neighborhood. And such things are called barriers. Okay, so you need some negative preserving harmonic functions, negative sign preserving subharmonic functions on the pointing, and that we define to be as the regularity of this function. So we will proceed this definition of barrier function, and then define the regularity of d omega, and using the regularity we will show that u equal to g on d omega if every point satisfies that regularity assumption. So I'll stop here, and we'll continue in the next lecture. Thank you.